name of Almighty God, I am Mahsa Sankosha, and today I want to talk about domain equations for tertiary current distributions using the Nernst Planck equations and electroneutrality. The domain equations can be derived by starting with the Nernst Planck equations. The material balance equation for each species I in the electrode is given by the continuity equation, with a flux given by the Nernst Planck equation, which is a derivative of the Ci based on the time plus delta Gi plus Ciu is equal to Ri total, where Ci denotes the concentration of the species I. SI unit is molar per cubic meter, U is the velocity vector, SI unit is meter per s, and the Gi denotes the molar flux related to the convective transport. See the equation above. The material balances give one equation per unknown species concentration. The concentration gradients are not assumed to be neglected here, and so the contribution of ion diffusion to overall current density can be non-zero compared with the domain equations for primary and secondary current distributions. There is one more unknown dependent in the variable, the electrolytic potential, which requires an additional equation to close the system. This equation is the electroneutrality condition, which follows from the dimensional analysis of Gauss's law. In a typical electrolytic solution, it is accurate over lengths greater than a few nanometer. When there is sigma Zi multiply Ci is equal to 0 using the electroneutrality condition reduces the number of dependent concentration variables by 1. Further, by combining the electroneutrality condition with the sum of all species flux vectors and the species mass balance equation multiplied by the individual species charge results in expression for the current vector and a current balance equation respectively. The expression for the current density is electrolyte IL reads the blue formula, whereas current balance in the electrolyte used for solving for the electric potential then becomes as follows, where QL can be any source or sink. QL is typically non-zero for porous electrodes. These formulations are also valid for the poor electrolytes in porous electrodes, except for the transport properties that have to be corrected for porosity and tortuosity. In such cases, the source of zinc UL denotes the charge transfer reactions in the porous electrode, and or for non-Faraday source or sink due to double layer charge and discharge. The charge transfer reaction can be parameterized by arbitrary functions of the concentrations of the species in the redox coupled and the local electric and electrolytic potentials. The most common way to describe the reaction kinetics is to use a Butler-Volmer expression for the charge transfer current density. See the Butler-Volmer equation. In the current balance in a porous electrode, the local current density multiplied by the specific surface area of an electrode gives a contribution of the source or CQL due to electrochemical reactions. Now I'm going to go through the mass fluxes and sources due to electrochemical reactions. When relating the species fluxes at an electrode surface to the electric currents, the general electrochemical reaction formula is as follows. It is used to define the stoichiometric coefficients Vi, with Vi being positive V reduction for products and negative V oxidized for the reactants in the reduction reaction. The number of participating electrons is N is always positive. The molar species fluxes Ni based on the SI unit is molar per square meter. S perpendicular to an electrode-electrolyte interface are calculated by summing all the flux contributions from the electrode reactions of index M according to Faraday's law, where I local M is the local current density based on SI unit is ampere per square meter of the electrochemical reaction. Nm is the number of participating electrons, and Faraday based on the SI unit is C based concentration based on the molar is the Faraday constant. Note that I local M denotes the current density perpendicular to the electrode surface. The molar species flux Ni is obtained from the normal component of the molar species flux vector over the electrode-electrolytic interface. Ni is equal to Ni multiplied by n, where n is the normal vector of the boundary pointing into the domain for a porous electrode. The electrochemical reactions result in species source terms calculated from the Ri molar is equal to minus sigma m of Vm, Vim, I local m divided by Nm, and for the constant where Vm based on the SI unit is square meter per cubic meter is specific surface area. Now I'm gonna go through the deposition, dissolution rates, gross velocities, and thicknesses on an electrode surface. The rate of dissolution or deposition on due to an electrode reaction is defined based on the reaction stoichiometry (VIM) and the local current (I local M) as described in mass fluxes and sources due to electrochemical reactions. If the reaction rate is known, the total gross velocity, deposition, and total based on the meter per second is defined as the sum of the velocity contributions for all species and electrode reactions according to velocity deposition total is equal to minus sigma. The Lau boundary is I mi divided by rho I sigma m Vim I local m divided by Nm for the constant where mi based on the SI unit is kilogram per mole is the molar mass and the rho I SI unit is kilogram per cubic meter. The density of the species I is the species index and m the index of the electrode reaction. This velocity can be used in deforming geometry models as a boundary condition for the geometry deformation by assuming that the solution or the position always occurs in the normal direction to an electrode boundary, with the velocity being directed into the electrolyte domain. Derivative x divided by time multiplied by n is equal to the velocity deposition total. In time-dependent simulation, one may also introduce a surface concentration variable C SI molar per square meter on the boundary and calculated the accumulated surface concentration change by using a local ordinary differential equation ODE based on the blue formula. The total deposited thickness S total M can then be defined as follows, where S total is equal to sigma I mi divided by rho I CSI. Stoichiometric coefficients for double layer capacitive charging and negative capacitive current corresponds to the accumulation of negative charge on the electrode surface and a corresponding counterbalance positive charge accumulating in the double layer. This can be understood in terms of conservation of current. Cathodic capacitive current at the electrode corresponds to the overall injection of negative charge from the double layer into the electrolyte, just as a cathodic Faraday current would add negative charge to the electrolyte through electron transfer. Consider an overall reaction as the blue formulas. This corresponds to a negative charge of 2 further constant being moved from double layer to solution. Following convection, that the reaction is written in the order of cathodic current as above. Then, with respect to the free solution species, the cation is a reactant negative stoichiometry and the anion is a product positive stoichiometry. This suggests Vi is equal to minus 1, Vx is equal to positive 1, and n is equal to 4 for an ideal double layer where both anion and cation have similar contributions to the double layer charge. Now I'm going to go through the film resistance. If a resistive film forms on the interface between an electrode and electrolyte, this results in additional potential losses. The model a film resistance an extra dependent variable for the potential drop over the film. Delta Vs film is reduced. The governing equation is delta Vs film is equal to I total and resistive film where R, which is a resistive field based on the SI unit is ohm, dot square meter is a generalized film resistance, and I total the sum of all currents over the interface. The activation over potentials Nm for all occurring electrode reactions on the electrode with the film resistive and extra potential contribution due to the film resistance according to the blue formula. If the thickness and conductivity of the film are known, the resistance can be written as the follow formula. Our resistance film is equal to S0 plus delta S divided by sigma film, where S is 0 is the reference initial film thickness, delta S the electrode thickness change, and sigma film the conductivity SI unit per S per m of the field. Now I'm going to go through the equilibrium potentials and the Nernst equation. Consider an arbitrary, possibly multi-electron step redox reaction involving a number of species SI defined as follow, where Vi is the stoichiometric coefficient of the reacting species of index E, I and N is the number of participating electrons. The equilibrium potential of the electron reaction equilibrium EQV is the electrode potential, the difference between the electrode phase and electrolyte phase potential Vs minus Vl, for which the net reaction rate and the local current density I local is zero. The equilibrium potential is directly related to the change of Gibbs free energy of the reacting species delta G as follows. E equilibrium is equal to minus delta G divided by N for the constant system. Free energy of the reacting species is concentration dependent. Also, the equilibrium potential is the concentration activity dependent. E equilibrium is usually defined according to the Nernst equation as follows. E equilibrium is equal to equilibrium and reference minus RT divided by NF ln multiplication. The lower bound is I divided by II and reference to the power of Vi, where the equilibrium reference based on the word is the equilibrium potential for a reference state for which all species activity II unitless are equal to a chosen set of reference activities II reference unitless. For ideal solutions, the activities are replaced by concentrations. Stockholm conditions correspond to reference concentrations of 1m for soluble species in the electrode partial pressure of a 1 atmosphere for gaseous species. Constant activities of 1 is used for solid metal species and solvents. Now I'm gonna go through the electrokinetics expressions. A number of different analytic expressions for the current density perpendicular to the electrolyte surface I local m are available in the following paragraph. The index m is dropped. All parameters are understood to refer to a specific reaction. Now I'm gonna go through the equilibrium potential and the over potential. The rate of the electrochemical reactions can be described by relating the reaction rate to the activation over potential. For an electrode reaction, the activation over potential denoted m volt is the following as follows, where equilibrium denotes the equilibrium potential. The Butler-Wormel equation, a common expression for the current density as a function of the activation over potential in modeling of electrochemical system, is the Butler-Wormel equation as follows, where alpha C unitless denotes the cathodic charge transfer coefficients and alpha R unitless the anodic charge transfer coefficients, and I zero based on the SI unit is ampere per square meter is the exchange current density. It should be denoted it should be noted that to use extensively for all sorts of reactions in the electrochemical community, the Boulter-Wolmer equation was originally derived for single electron transfer equation, for instance, implying that the reaction doesn't involve the breaking or creation of a chemical bond. Concentration dependence and exchange current density. The exchange current density is generally concentration dependent. For certain conditions, it is possible to derive analytical expressions for I0 assuming a concentration dependent equilibrium potential defined by the Nernst equation. See previous section equilibrium potentials and the Nernst equation. The kinetics to follow the law of mass action and the condition that alpha R plus alpha C is equal to n, then the exchange current density becomes I0 reference multiplication. The lower boundary is I. Velocity I is bigger than 0. I divided by I reference to the power of alpha C. Velocity I divided by m multiplication. Vi is less than 0. I divided by I reference to the power of minus alpha R Vi divided by n, where I zero reference is the exchange current density. SI unit is ampere per square meter at the reference state. The above expression can be derived from the mass action law, which gives the following expression for the local current density as follow, where the over potential and reference based on the SI unit is volt is measured using relative to reference state, which yields N reference is equal to phi s is minus phi l minus equilibrium reference. This latter form of the Butler-Volmer equation, where the reference effort potential and the exchange current density don't vary with concentration, is usually preferable numerically. The law of mass action is usually not suitable for defining complex reactions involving multiple electron steps. For certain multi-electron reactions where one electron transfer step is rate limiting, it is possible to derive a lumped Butler-Volmer expression using the following relation for the exchange current density. See the first reference. And as formula, we have a lambda I, which is a generic exponential coefficient. For this case, alpha I and alpha C may be independently defined by rearranging the Butler-Volmer expression using n reference similarly to what was done for the mass action law case above. The lambda I coefficients relate to the anodic and zeta I or cathodic and zeta Ci reaction orders according to the blue formulas. Now I want to talk about exchange current density and rate constants. In electroanalysis, one commonly defines electrokinetics in terms of rate constant rather than exchange current densities. For instance, for one electron redox couple of concentrations CO and CR with the same reference concentration C reference, while both species I0 and reference Co0 and for the constant C reference, the mass action law expression above can be written as the blue formula, where Co0 is based on the meter per second is the heterogeneous rate constant. Now I want to go through the generic concentration dependent Butler-Volmer type kinetics. This expression type gives more freedom of the user to define concentration dependent Butler-Volmer types of expressions, where the analytic and cathodic terms of the current density expression typically depending on the local concentrations of the electroactive species. The electrode surface can be individually defined as follows. Here CR and COR dimensionless expression describing the dependence on the reduced and oxidized species in the reaction. Note that if CO is not equal to CR, when n is equal to 0, this kinetic expression results in I local is not equal to 0, thus violating the concept of equilibrium. This may result in thermodynamic inconsistency, for instance, when coupling an electrochemical model to heat transfer. Now I'll go through the simplification of the Butler-Volmer equation. Linearized Butler-Volmer, the charge transfer reaction can be expressed by a linearized Butler-Volmer expression, which can be used for a small potential n is very smaller than RT divided by Faraday constant and is usually referred to as the Lau field approximation. This approximation gives the following linearized equation. I local is equal to I0 alpha R plus alpha C multiplied by Faraday constant divided by RT multiplied by anodic and cathodic Tafel equations by assuming either high anodic or cathodic overpotentials for a given current, that is, slow kinetics or low I0. One of the terms in the original Butler-Volmer potentials can be neglected. The anodic Tafel equation is implemented as follows. I local is equal to I0 dot 10 to the power of n divided by RR, where RR is based on the SI unit is based on the volt. The so-called Tafel slope RR relates to the corresponding transfer coefficient as follows. And the cathodic Tafel expression is defined according to the blue formula, where the sign accounts for the negative cathodic charge transfer current. Here IC is required to be negative and relates to the transfer coefficient according to alpha C is equal to minus RT ln 10 divided by alpha C Faraday. Thank you so much for watching my tutorial video until the end, and